Cool. So I'm Avinash Idnani. I'm an engineering manager at Rokt, and I lead the ML infrastructure team there. So today I'm going to talk to you about scaling machine learning at Rokt and why we built a custom feature store. So before we dive in, we basically are going to understand what Rokt does, why machine learning matters at Rokt, what was some of the scaling pain that we encountered while going through the journey without a feature store, why we decided to build our own feature store. Then we dive into some of the details of the architecture and the overview of the different machine learning flows and how feature store helps, and then the impact on the ML at Rokt essentially of the feature store. And then finally, I'll leave you with some of the lessons learned, so maybe you can benefit as well. So let's dive in. So what is Rokt? We personalize e-commerce at scale. So basically, we are an e-commerce technology company. We're not an e-commerce company. We don't sell anything. We connect global e-commerce in the moment that matters the most, which is essentially what we call the transaction moment. It's the moment you're trying to purchase something. So that transaction moment is basically defined as your selection page, your cart page, your payment page, your confirmation page. And what we help e-commerce companies do is add it, like essentially get ancillary revenue. So that's additional revenue on top of what they normally sell, and also help acquire customers at scale. So if you can see an example here, we've got a listing on the selection page that's powered by Rokt. Same on the add to cart page, we could give you an upsell offer for parking. On the payment page, there could be a credit card offer. And then finally, on the confirmation page, you could get like some subscription offer potentially. And this is the additional revenue that we will help our e-commerce partners with essentially. So it's been 14 years in the making, and we've found some great partners and advertisers to business with. You might have seen offers from HelloFresh or Apple when you're checking out on Hoyts or Domino's or Wilson's Parking. So this year we're looking to power more than 7.5 billion transactions across all our e-commerce partners. And we have about 400 million unique customers visit our SDK, which is on these e-commerce partners. So moving on, great. So I think you understand what Rokt does to some extent. Let's understand what was the secret sauce that has powered our success, and that's machine learning. So essentially, what it all comes down to is relevance. Relevance in the moment when you're purchasing something. So how can we provide value to all the three parties involved? That's the e-commerce partner, the advertiser, as well as the customer. And it can only happen if that content is truly relevant, like it feels native, it's helpful, it's timely, and not like a pop-up ad, essentially. So what do we have is essentially we got first-party data from the e-commerce site. We got customer insights from our advertiser. And then we got these different UX options, basically, that the advertiser can say they want to show to the end user. And we combine all of this in real time, and then we feed it to our deep learning models, which will score thousands of these combinations and pick the one that maximizes engagement and value. The result, well, it's a very personalized native experience that's powered by AI that feels seamless and not spammy. So how do we do this, basically, and why does this demand machine learning at scale? So the richer the personalization, the more the context you need. We need to know more about the user, their purchases, their behaviors. That way we can better predict what might be relevant to them. Second, to make sense of all this context, we need more complex machine learning models that can identify subtle patterns and maximize long-term value. Lastly, we have extreme latency constraints, which is probably a unique challenge for a few partners like Facebook and others who display ads. So we score thousands of these candidates in real time, and we must return the best ranked options in under 250 milliseconds. So this is just at the current scale. We're obviously adding more advertisers, which means we have more offers. We have more data about the user as they go through more e-commerce transactions. So the number of combinations explodes, the data we have explodes, which makes the system's demands over time much more complex, essentially. And this is why we needed to scale machine learning at Rokt, essentially. So just to help you understand our maturity curve, our ML maturity curve, and how our infra kind of lagged behind every time, and why we've decided to invest hard on machine learning infrastructure, and why I still have a job there. So initially, we started with rules-based logic on the left in 2014, 2016. It was basically batch inferencing, not a big infra requirement at that time. We then moved on to slightly more complex models and logistical regressions. We introduced real-time scoring, so now we're doing inferencing in real time. So feature logic at this point became fragmented. It was spread across training pipelines and serving and notebooks. We then went on to more richer models and gradient boosted trees. And this kind of exposed the training serving skew, which I'll touch upon later. We lacked standardization, debugging was painful, and with deep learning, that complexity just explodes, right? So you got more features, more embeddings, large input volumes, and that puts a lot of pressure on the infra. So reproducibility and scale are now extremely critical. So this whole journey made it clear that we needed some serious investment in the ML infrastructure area, essentially. So moving on, let's talk about, before we build a feature store, what really hurt us and why it's critical to Rokt, essentially. So I think most of you should know what a feature is, but I thought, for people who don't, let's quickly recap. So features are structured signals that ML models learn from. So you got the raw data on the left, which is like emails or text. And then you do some transformations, which is basically your feature engineering. You would do a join or a transform, or you would aggregate. And then finally, you get what you call is clean transform data that is basically, what were the number of emails that, you sent today? Or have you used attachments recently? Or what's your most used email domain? So those are the features that come out of raw data. So this is going to be really important to understand the content that follows next, and I'll also introduce what a feature store is. So moving on, we spoke about feature engineering. Like, what was life without a feature store? Well, it was messy and it slowed us down. Why? So duplicate logic all over. So the same feature transformations could be written in SQL for training, and then when we're serving the model online, they're written in Go. Inconsistencies and confusion and bugs. Then there is the big problem of training serving skew, which you might have heard several times potentially if you looked at ML, which is a very core problem. It's the worst kind of bugs, right? So you run a model offline, it looks great. Then you launch it online and it just doesn't work. And that's because your features are inconsistent across training and serving. And that debugging that is an absolute nightmare. So we also didn't have point-in-time correctness. So point-in-time correctness is basically when you're training your model, you shouldn't look at future data. So what was the snapshot of your data at that point in time? If you give your model future data, that becomes basically a model seems like it's accurate, but it cannot generalize. And that's a big problem. So we didn't have point-in-time correctness. There was no clear ownership. So, people would create features in notebooks. People would create features in services and training. Nobody knew who was responsible for what. And so all of this meant our debugging was extremely slow. I think we once spent days chasing a regression, which was basically a small difference in training and serving features, essentially. And that's an example of skew. So basically, as something as small as in your training set, you have a certain definition of what the email domain looks like, but in your serving set, you decided to add that to upper, which is of course a bug. But all of this became a huge bottleneck as we tried to scale, and it pushed us to rethink what we do for feature engineering, essentially. So let's understand the real impact of getting this wrong. So I think on the left, you got tangible losses. So dollar values of like what we've really encountered in our journey. So one of the bug fixes we had led to like a $5 or $7 million gain over time. So it was basically lingering around for a while. And once we fixed it, we noticed we could have actually had a potential revenue uptick of $5 to $7 million. Another single training bug cost us like $170,000 just from one mistake in one model. On the right is the intangible cost, which is actually a bigger cost to any business. Debugging is a nightmare, so you don't know what's going on with your system. Reproducibility was shaky, so trust in our pipelines is very low. Like our data scientists and ML engineers are like, is this going to work? And all of this made it slower to experiment and iterate, which meant fewer wins for the business. I think this was the big punch where this has convinced us to basically fix the foundation before we could scale confidently. With deep learning and the number of features involved, if we are in this state, we're basically going to go ad hoc and we won't know what's happening. So what we needed, and this is kind of 5 different things that I thought I should share in order to scale confidently. Right, so a shared definition for every feature. Basically, we might have 3 different people come up with 3 different definitions of email domain, and that isn't right. We needed point in time baked in. Like no one needs to think of, whether I'm looking at future data or not, or we're leaking data during training. Like that should just not happen. The system shouldn't allow it. Training serving consistency, which we just spoke about. We don't want features to behave different offline and online because otherwise your model is doomed. Self-serve onboarding. So a lot of the times we want our data scientists and ML engineers to iterate quickly and do it independently. I think autonomy is a big thing. Otherwise they're dependent on other teams and that just slows us down. Finally, there's clear ownership and lineage. So who built this feature, right? When was it changed? What model used it? And we had no idea prior to a feature store. So these sound simple, but they're foundational if you want to scale ML without things breaking silently. And if you're not tracking metrics, which someone mentioned earlier, it's really difficult to understand what's going on with your model. Cool. So this is where it all ties together. And this, I said I'll introduce the feature store to you. So this is exactly the requirements that we had for a system called a feature store. It gives us a single source of truth for all features from training to real-time inference. We define once logic is consistent across environments, features are versioned and point-in-time correct, and teams can self-serve, so there's no more handoffs between teams. So on the right, there's a diagram that kind of gives you an overview of a dumbed-down feature store. It's a lot more complex than this, and I'll show you, I promise. There is the transformations, the registry, the storage, and the monitoring that it helps with. And then more importantly, you make sure that your training and serving is seeing the same set of data or the same set of features. Cool. So coming to why we chose to go bespoke. We were seeing, we needed a feature store. Should we build? Should we buy? We saw Meta and LinkedIn kind of build their own, but they took years to build it. So we were like, should we actually go bespoke because it's a big investment? So we obviously did what any reasonable small startup team would do. We looked at what was already out there. There were several mature feature store solutions, and they've come a long way today. When we were doing this, it was back in 2020, 2021. I think one of the biggest requirements for Rokt is that we don't have a stable user ID. So when customers or users come into an e-commerce platform, they don't log in like they do on Facebook or Amazon or Google. So we got a user who we only know some pieces of information about, like emails or phone numbers. And what we do internally is we have an identity system that ties these up together. So we'll stitch up sessions that they've been on in the past. And this is the big requirement, is that we needed these feature stores to be able to query on multiple of these session keys. And a lot of them were single join keys. And so that was, I think, one of the key requirements that a lot of feature stores were missing. The other thing was we needed real-time transformation. So I explained the 250 millisecond latency requirement. We also needed to run, when we fetch data for these sessions, we needed to then do some transformations or operations on top of that. And these needed to be run in under 60 milliseconds because that was our feature store latency requirement. And a lot of the solutions either didn't have on-demand transformations or they didn't have, they didn't support the 60 milliseconds. Finally, there was, we had missing key data types, so arrays and timestamps were very common, but a lot of them didn't support them back then. And then it was, I think the integration was non-trivial. So it was a very big lift to get, orchestration and infra reshaping to plug into our stack. And that felt like a step backwards to us at that point. So to drive this point home, I thought this would help, and I don't know why my slide is broken. But essentially, we explored off-the-shelf tools, we ran POCs, we tested capabilities, but often ran into roadblocks. It didn't align with our architecture, and we would have, if we were to adapt them, we would require significant compromises. So we chose to build. Why? Because we wanted to go faster, we want to integrate deeply with our stack, and then prioritize what mattered to us rather than depending on vendor roadmaps. Cool. So let's dive into what's inside our feature store. So let's look at the architecture. Like I said, it wasn't trivial. So this is a very high-level architecture of our feature store. It's a large system. It spans batch and streaming, training and serving, and every green box is something we built, essentially. So we're not going to dive into every piece here. I'm going to try to break it down in the next few slides to focus on 3 key workflows, which is how do you experiment with a new feature? How do you productionize that feature? And then how do you see it in real time? So the first one is new feature experiment. So one of the first things that any data scientist or ML engineer wants to do is test the new feature. So he should be able to easily define it and then see its impact on the model in training. So in our feature store, we have something called the domain specific language, or DSL, which you may have heard of before. That helps define the features. These are then put through to a feature registry, which captures these features. And this is done in a local namespace, so we don't affect prod environment. One can simply also define a feature in a notebook, which we added much later, but that makes we don't have to go through the registration flow. Once the data scientist defines the feature, he can then load it in his notebook, and the SDK is basically what helps compute the feature, essentially. So it knows how the SDK knows, based on this definition, what am I supposed to fetch, what am I supposed to transform, and so on. And the pink box there on the right shows the improvements we've made since the MVP. So we introduced local namespaces, we simplified the DSL, we added some validation to improve the developer experience and as well as avoid any issues with live production features. Cool. So the next part. So once you've defined a feature, the next step is, okay, how do I test this feature in a live A/B test, essentially? So the first thing you would do is you would change that namespace to production, and you would say, okay, now I want to set a schedule and I want to start serving this feature online. So some of the data then needs to be put to an online store. So if you remember, we have a very strict latency requirement, which means we can't serve off data lake or I guess Kafka would work, but we can't serve off offline stores. So we need this data to be in an online store, and a service called the materializer there would understand that this feature needs to be pushed online or needs to be served online. And it would trigger these materialization jobs on Spark on Kubernetes. And then that would fetch data from Data Lake or Kafka and push it to Cassandra or Elasticache. So since the MVP, we have migrated from EMR to Spark on K8s for better scalability performance. We had use cases which had 1 billion of roles that needed to be materialized through the online store. Additionally, we switched from DynamoDB to our own Cassandra cluster. This was primarily to reduce costs because our read and write volume was going up as we added more features. So coming to the final bit, so now you have your features in an online store. What do you do next? You want to live A/B test your model with this new feature. So going from the right, you got an upstream service that calls this online API to get features. This API already has a pre-fetched DAG, a directed acyclic graph of the full set of features that are needed online. The DAG ensures that we're computing all dependent features first and there are no redundant computations. The Go SDK then knows what to do with the features. So should I go fetch data from Cassandra? Should I use the context that's been given to me in my request? And then it hands it off to a UDF executor, which is a user-defined function executor. So if you had some Python code on top that you wanted to transform something that you fetch from the online store, you could do that. So that's the function of the UDF executor. And all of this, it returns in under 60 milliseconds, and it has consistent logic with training. So that kind of covers the flow. In terms of improvements, it was a strict latency requirement, and the UDF executor became a bottleneck because it was written in Python. We migrated to Go. We started using PyGo there to improve concurrency and reduce timeouts. We also boosted availability and latency of all the services in green there over the once we had migrated all the features over. So that kind of covers the 3 different flows that we have and gives you a feel for the architecture. Next, I just want to go back to how this helps and why it's important for ML engineers and data scientists. So we'll cover each of these areas, but essentially feature development. Previously, you had manual SQL and custom Go per model. Now you have these reusable features which you can use across models. In training serving, you had logic drift previously. Now you have the unified logic because of the SDK. Experimentation, so people were dependent on platform engineers to write the features on in the Go application. But now you have self-serve A/B testing, reproducibility. So we got point-in-time correctness, we got traceability, we got versioning. And then finally, we don't have features scattered. It's all in a central registry with lineage and ownership. So that's what Feature Store gave us, and that's why we're now able to scale very confidently. Another slice of this is to look at it across the ML stack. So how did it help with experimentation? Well, we spoke about local namespaces and self-serve A/B tests. Training, you get to reuse features. You got point-in-time correctness snapshots. Deployment, you don't have to do anything but just say, hey, I want to promote this to production, and the features just served. You got the auto materialization, so you don't have to do any work to move it to an online store. For serving, there are guarantees on SLOs of P99 at 60 milliseconds. You got unified logic with the shared Go SDK. And then finally, there's easier to monitor and debug, essentially. So in short, Feature Store for us isn't a sidecar. It became the backbone that powered consistent, scalable ML from start to finish. And finally, we've spent 3 years building and evolving our Feature Store, and we've learned a lot along the way. And I'll share some lessons from that journey that might benefit you. So if you want to take one thing away, and if you do ML at scale, or you're starting to do ML at scale, definitely consider a Feature Store, because it can be a game changer for innovation and how quickly you innovate. If you do decide to invest in a Feature Store, you got the same options that we did, which is either to buy or to build. I think a lot of off-the-shelf tools are good enough for 80% of the use cases, and they're evolving rapidly. But you could hit some custom limitations if you have very niche use cases. If you're like Rokt and you have a very unique use case, as I shared, we don't have a global ID, then you may want to build. But I think one thing you need to understand is it's a long-term investment, and it should be treated as core infrastructure. And that's what we're doing at Rokt. We're making sure that we center a lot of things around our Feature Store, and we invest heavily going forward as well. So it's been 3 years, and we're still improving that offering right now. So yeah, I think that's all I have for you today. We have a booth set up, so if you want to come chat with me, talk about this, that'd be great. Thanks for giving me your time, and I hope you guys gain something from it.